Cadence and simulations. Take it away, Tom.
Thank you for having me. Yeah, Amy kind of walked you guys through the kind of the overview and the motivation for doing NEOCam, and I'm going to basically walk you through in gory detail how we're actually going to do the on-sky survey itself, what all the different steps are in building up our sky coverage. Again, like she said, there's a bunch of people who have been working on this. There's not a few people. It's a great team, and I'm really happy to be working with all these people. So basically, the fundamental units that we're going to be working with in NEOCam is the 180-second visit, which consists of 6 dittered exposures, which are basically collected in a hexagonal pattern, 10 arcsecond ditter steps between each of those exposures. They get summed up into a visit, which is really the the deep cadence that we're going to be looking for our NEOs and other moving objects. The the reason why we're doing the ditters is because that improves the astrometric accuracy and enhances our robustness against bad pixel cosmic rays. That means that the image just looks better. And Rock Kutri, who's going to be after me, is going to go into some of the things we can do there. The visits is our main workhorse for getting our moving objects, our NEOs, but we have access to the exposures. So that means that we can go in and look for fast movers in that data. After we've taken one single visit, basically the way we go about covering the sky is we start down here in the lower right. That's our first visit. Then we move over in the short direction to the next visit, and we just move in the longitudinal direction. About 16 visits, we can adjust that number. We can do 15 or 17 depending on what makes sense. And then we basically do one move in the long direction of the field of view. And then we come back and return back to our first exposure. That is what we call the loop, and it takes about 2 hours. There's a little bit of overlap between adjacent visits, which means that you can, occasionally get objects in those overlaps that gives you extra detections. The reason why we're doing these loops, and we do them 4 times of the same patch of skies, that allows us to build these quads, which is where we generate our 4 detection tracklets. A quad takes 8 hours to finish. That means that each tracklet has a 6-hour baseline, 0, 2, 4, 6. And the quads are basically the industry standard that allows linking tracklets together with high efficiency. It's been done, Panthers does it, Catalina does it, WISE uses 5, and we have the ability to turn quads into quints if we would need that in order to maintain a really high efficiency. Okay. That gets gotten us one of those quads. The way you basically now do is you start either at the bottom, at the low latitude. So our field of regard is basically the area we can cover is from 45 degree solar elongations, as close to the sun, all the way out to 120 degree solar elongation. Note, however, that I say here, a stack like this takes 2 days. So there's a little bit of time lapse that happens. You basically do one of those quads, you move up a long step, do another one, you move up, do another one, or you can start at the top, move your way down. Basically, in order to cover your entire field of regards, now we need 3 stacks. And aside, that's just basically these stacks. Now you have, that takes about 6 days. Note that when you do these type of simulations, and we've been running these, these type of patterns through our survey simulator, looking for which objects it shows up in it, counting them up to get our completeness, just like Lynn was talking about in her simulations. It really matters which direction you search, where you start and where you end up. Because there's a couple of things that happens. If you start at so on the trailing sides, going behind the sun, you want to start at your highest solar elongation and move towards the sun, because that's the direction the asteroid's moving. That also means that as you're going over, you're actually not covering, so I apologize, that should be 120 to 45. But what's happening is that when you start 120 and you go towards the 45, like 6 days, that means that the sun has moved 6 degrees. And so you're actually not covering 75 degrees, you're actually covering 81 degrees. So you're always chasing the sun on one side. And then on the other side, you start at the lowest solar elongation and move away from the sun. The sun is then following you. But even then, your 120 degree solar elongation over those 6 days has moved 6 degrees. So you're chasing that edge as well. And basically, that little effect of which direction you go changes your completeness by a few percent over the 5 year. So basically what we do then, if we just alternate, here's the sun, the earth, and NEOCam and L1, and we just alternate between the two sides. You can think of this as a rotating frame. And basically we do one side, the other side, one side, the other side. And can we start this video here? Or do I just click it? There you go. So this is basically just how we build it up. You go through, create these loops, quads, stacks, and then basically you do one just, a little bit longer, and then you work your way down. And then when you get to the bottom, you simply work your way up again. And we do this over and 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 over again for the 5-year baseline mission. And hopefully we'll, get extended for another 5 years, and we'll do it for 10 years. And it's the same pattern over and over and over again. Known pattern, we know how to work with it, and so forth. So basically, I want to emphasize that NEOCam is optimized for NEOs. It is, optimized to achieve the congressional goal of 90%, of 140-meter objects. That, of course, doesn't mean that we'll only see 140-meter objects. Our simulations say we will detect about 300,000 NEOs smaller than 140 meters. This will be a really rich data set. Not only that, we will see thousands of short and long period comets. That means we will be able to say quite a bit about the residual risk after the retirement of the 140-meter risk that lies in mainly the long period comets. And also, we have the ability to focus on and optimize our survey for orbital quality and physical characterization, making sure that we meet this requirement of diameters between 15 and 25%, and make sure that the orbital quality is good. It's designed for cell follow-up. That means that most NEOs larger than 140 meters are seen dozens of times over the 5-year mission. You can see here, there's a plot that shows that while the peak is at lower number of detections, there are a large number of NEOs that are seen 20, 30, 40, 100, 150, 200 times during the 5-year mission. And we cover quite a bit of phase angles. That means we can go and actually do physical characterization, look at how phase effects and stuff like that, affects the NEOs. We have made sure that the cadence is optimized to get good orbits. So this is basically just taking 5 years of the MPC catalog, and that's in the gray line there, and basically saying if you only had 5 years of observation taking the minor planet catalog for the NEOs, what would those orbits look like? Not what the orbits are, over 25, because we want to compare a 5-year survey to what, is done over a 5-year period now. And you can see that our 3-year survey actually is comparable to the 5-year MPC catalog, and our 5-year survey is a little bit better on the orbital quality. So to conclude, this is an optimized survey for NEOs. We have control of how to actually optimize it. We can change all these parameters, quads, the quints, how many fields we do in a loop. You can change the extent of the loop by adding more, visits in there and things like that. And that we can use all those now to basically make sure that we know how to link these objects at high efficiency. We can get good orbits, and we can get good physical characterization. And we do basically that by using our NEOCam survey simulator, which allows for basically performance using the reference model. I want to emphasize one thing that Timothy mentioned yesterday, that when we get this survey out, you can finally start doing all your simulations for 140-meter objects rather than for H22, because we'll have the H converted into diameters and albedos. And we can get past this, is it H of 22 or H of 23 or whatever is the conversion. And we've done a bunch of papers looking at different things with the survey simulator. So this is active work, and that's it. Thank you.
Thank you, Tommy. So, Dave, do you have a question?
Yeah. How is the dithering accomplished? Is the whole telescope bore site being changed?
Yes.
How much overhead is there in, how much time does it take for the telescope to settle so that you can actually take that next exposure?
I think it's on the order of a second or so.
Reaction wheels?
Yes.
Okay.
Correct me if I'm wrong on the last question. What? Yes, so it's exposure is 30 seconds. I think the exposure time is what, like 29 seconds or something like that. Yeah. Yeah, they're really fast. It's no overhead almost at all.
Okay, any more questions? Great. Let's thank our speaker again.